Hello everyone, this is our first video on forces, with me at least. You have done a little bit of forces with Matthew, but now this is our first video on forces, and we're just going to do a brief discussion about Aristotle's theories and some other historical theories on force, a very European, Eurocentric perspective on force. And then I will provide you with some reference videos that I would like you to watch regarding some of these ideas. So we're going to talk about three individuals right now. We're going to follow the traditional European, direct line, which is Aristotle, Galileo, and Isaac Newton. These are three different scientists that appeared through Europe through the last millennia, I guess, almost 2 millennia, I guess, 2 millennia essentially. And they all had interesting ideas about force and about how objects move and why they move. So Aristotle was a Greek philosopher, and he's attributed with these ideas. He suggested that falling bodies would fall at a constant speed. So if you drop something, it falls at a constant speed. Now, Aristotle was a Greek philosopher, not a scientist, so he did not do any experiments. So he did not realize that this is not true. This is bad. This is an untrue thing. So if you actually drop something, the farther you drop it, the faster it will be going most of the time. Falling bodies fall faster if they are heavier. This is also something that is later discovered to be false. False. Even though it might seem that heavier objects often seem to fall faster, it's usually because heavier objects have less air resistance. Falling bodies fall slower when they are not met with resistance. So again, another false concept, but a good idea to realize that there is some difference between heavier and lighter objects, but it was actually a lot more challenging than just saying that heavy objects fall faster. And he also noted that every object on Earth seemed to have a natural motion, as he called it, or an attraction towards the center of the Earth. No matter where you drop something, it seems to drop towards the center of the Earth, and that was probably a pretty impressive discovery in a way, or maybe an obvious discovery, honestly. But this is the idea of gravity, right? So even though he's just a philosopher and he's just walking around thinking most of the time and just talking out loud and people are listening to him, he did at least come to conceptualize the idea that things fall downwards, and this might be because of some sort of natural motion or some sort of attraction to the center of the Earth, which we have much better idea about nowadays. And he also concluded that you must apply a force to move an object. Great, that's true. If I want to move something off my desk, I have to push on it. And he also said that you had to keep applying that force. And so I suppose he had never played hockey before, because I know that if I perform some sort of slap shot or whatever with a puck, that puck will continue to slide across the ice without me applying force. So and in fact, with something like a puck on ice, it might slide for a long time, or perhaps a pool playing billiards, and a billiard ball will glide across the table for a long period of time, even though you only hit it once. So the idea that it requires the application of force actually is another idea that he was wrong about. This is a false idea, and it doesn't get corrected for quite a long time. Galileo did not agree with Aristotle, so this is, of course, 2,000 years later pretty much, but he says that once you stopped applying a force on an object, it is friction that stops the ball, and friction is yet another force. So this is the idea that it requires a force to make an object move. So force is required to cause motion, and force is required to stop motion. And this is one that I find that students always get confused, is they don't think about the idea that there is actually a force acting on an object that stops it from moving. And this is where traveling through space is real easy, because in traveling through space, as soon as you apply that force, you don't have to apply any more force. You'll continue to travel, and unless you hit something, because there are no other forces in space except for maybe gravitational forces. So, and also why you can do things like make solar sails and things that use very, very light, very, very little amounts of force to travel. Anyways, that's a whole other point that we can talk about another day. So friction will slow the object down to a complete stop. So an opposite force is required to slow an object down, or slow motion. And a body in motion will continue in motion at the same speed unless a force acts on that object in the opposite direction. So that's the idea that once you apply a force, the object will continue in motion unless another force is added. And he then said that in a vacuum, a place where there would be no atmospheric pressure, and all forces of air friction were removed, all objects should fall at the same speed regardless of their mass. And this concept is really awesome. We are going to watch, I'm going to point you out to a video. So there is a video on with the video of bowling ball drop, bowling ball feather drop. I will link that in the Google Classroom. You must watch this video. I've watched it possibly over a dozen times now, and every time I get chills. It works so beautifully. This idea that only Galileo could conceive of, right? He could only imagine this was true. He could never perform this experiment because he had no vacuum to work with, but he was able. But the idea that we could confirm this experiment in 2000 and whatever, with a massive demonstration is unbelievable. It's an unbelievable achievement to be that we are in a place where we have the technology to now perform this experiment, and it works. It actually works, and works amazingly well. So an object falling freely through the air or rolling freely down an inclined plane will also undergo a constant acceleration. So this was his attempt to do the same sort of idea. He said, well, okay, I don't have a place where I can remove all the friction, but balls rolling don't really have a lot of friction. So he created a whole set of objects, which they call what do they call? They call them Galileo's inclines or whatever. And I will also post a video about that where there's a man who's made a whole bunch of these, and he shows you some really fun things where, you know, he drops these balls and you think, well, there's no way that the ball is going to, you know, the ball, I think they have a plane that looks like this, and he drops a ball here, and the ball falls and it ends up at exactly the same height, even though the shape is so peculiar, right? You think that it shouldn't be able to make it that high. And it doesn't matter if you start here or if you start there, it will end up at the exact same height. And there's a whole bunch of examples of this. So I will also link a video about this. These are the, oh, now I lost the name of them, but they're also a video. Okay. And so please watch those two videos, and we'll have a little brief check-in about those. So one of the experiments Galileo performed was motion involving rolling objects down a U-shaped incline and measuring the height at which they traveled. Galileo predicted that in an ideal scenario, the objects would accelerate along the inclines until it reached its original height. And this works. Now, he wasn't correct about everything. He did find a lot of things that were true and a lot of different ideas. He, of course, is one of the ones who's attributed to the heliocentric model of our galaxy, where our universe, where we have the sun at the center and all the planets around it, and you know, the story of him being trapped away because of this idea, although heliocentric ideas were everywhere else in the world, just not in Europe, and all that sort of stuff. So he is a very famed European scientist. Now, we're going to go from Galileo into Newton, who's a little bit of a later scientist, more recent, but not that recent. And Newton describes acceleration as an imbalance of force. So he really is looking at things from the perspective of acceleration, something we've just discussed how to calculate. And he says that acceleration is really the result of forces. So for example, if there is a force acting on your right side, but there is a stronger force acting on your left side, you will move to the right. And this movement to the right is an acceleration to the right because of the imbalanced forces. And so he has 3 laws that we are going to cover, with the first one being the law of inertia. An object at rest stays at rest, and an object in motion stays in motion. And I believe we're going to do another video about that, as we have a couple of videos to follow up on for these first ideas from Galileo's ideas. So we'll watch those videos on Galileo's ideas, and then I'll do another brief video on the Newton's first law of motion, the law of inertia. And then we'll follow that up with a video on the laws of unbalanced forces. And then the final law, which is escaping me right now, the law of, that's the second law, imbalanced forces. And the third law, which is the law of equal and opposite reactions, of course. All right. Thanks for listening, and we'll talk to you soon.